Welcome to Menus and File Management, the second half of the first class, Introduction to SolidCAM. In the first class, we discussed the SolidCAM settings. If you've not yet gone through the first half of Introduction to SolidCAM called the settings, we highly suggest that you look for the video on the SolidCAM website or ask your local reseller about it. Let's begin today by starting a new CAM project by either going to the SolidCAM tab on the SOLIDWORKS ribbon or up to the top and select SolidCAM, New, Milling. When a new CAM project is started, the SolidCAM executable will launch in the background and stay running until you close SOLIDWORKS or SolidCAM. If Use Model File Directory is checked, it will create your CAM project files in the same directory as the SOLIDWORKS file it is referencing. If you prefer to create your CAM project files in a different location, unselect Use Model File Directory and create a path to the new location. The default path is the first setting you changed in the SolidCAM settings called User Directory for CAM Parts. The name given to the CAM project defaults to the name of the SOLIDWORKS file. This can be changed now or it can be changed later by using the Save As option. I personally like to keep my CAM project files in the same location as my SolidWorks part. However, we recognize that some companies might have specific protocol for file management. In that case, you will likely need to path this to a specific location. The model name directory shows the name of the file and where it is located. I am defaulted to inch for my SolidCAM settings, so I will select OK. The first thing that happens is that a SolidWorks assembly is automatically created, and we are now running in assembly mode. The second thing that happens is that SolidCAM created a perfect copy of the original part and put the original part away for safekeeping. The copied version of the original SolidWorks file is called the design model. Any revisions to the original SolidWorks model will be automatically propagated down to the design model, provided that the option was set in the SolidCAM settings. Since we are now working in assembly mode, you have the option of working on an entire assembly or multiple parts in that assembly, and you can also import any fixtures like a table, vise, parallels, etc. that you may want to use for gouge checking or selecting the part levels from. For all new users, I suggest working in manual mode. I always work in manual mode because I prefer to see the revisions made to the model and which toolpaths were affected by those changes. If your system is set up for manual mode and revisions are made, you will see the familiar SolidWorks red and green stoplight icon on top of any toolpath that was affected by that particular revision. You may also see the icon over the stock or the target if they require synchronization. Provided the SolidCAM settings are correct, the design model will notify you if changes are made to the SolidWorks file. If you want the design model to affect the SolidWorks model, this would require you to copy the design model out of the CAM folder, rename it to the original SolidWorks file, and overwrite the original SolidWorks file. Off to the left are the CAM part definition options. This is where we will set up which machine we're going to create this CAM project for, define our coordinate system or systems, and select our stock and target. The machine controller can be changed at any time, but since we already have it defaulted to our preferred post, we'll start by creating a coordinate system. Clicking on Define opens the coordinate system page. Currently, there are 4 options for creating a coordinate system. At the bottom of the list, Normal to Current View allows the model to be oriented on the screen for maximum cut or reach, where you can then capture the current view. This option is very useful for 5-axis porting. The next option, Up, allows you to use any coordinate system you may have already created in SolidWorks while designing the part. Above that is Define, where you will be prompted to select the origin, then the X direction, and then the Y direction. Select Face is the system default when you first come into the coordinate page. This is arguably the easiest way to create a coordinate system. Since it is the default, simply select a face on the part to orient the Z-axis perpendicular to that face. Then you can use the Pick, Flip, Delta, or Rotate Around Axis commands to further manipulate your coordinate system. If Select Face is highlighted, then there will also be a drop-down box labeled Place CoordSys Origin To. Whichever option is shown in the drop-down box is where the coordinate system will be placed. When the part face is selected, SolidCAM draws a minimum extents box around the design model and adds asterisks for easy selection for an origin location. These are temporarily displayed for the convenience of selecting the true center of a particular side. Once you have placed your coordinate system, you can then select the green check at the top left of the screen to finalize your selection. The CoordSys data page has several options, but there are only 3 values you need to check unless you're doing multi-axis machining. The 3 values that should already be set, but are always a good idea to look at, are clearance level, part upper level, and part lower level. Clearance level is the rapid plane, which should be set to 1 inch above the upper level. If the part upper level is set to 1.5 inches, then the clearance level should be 2.5. The clearance level default can be changed by going into the SolidCAM settings under Units. The tool start level should be set to 5 per the first video called the settings. The tool start level should not be turned on in a 2 or 3 axis post unless requested. This value is used for a special tool change point. I like to set it up and out of the way of the clearance level. If the clearance level ever exceeds the tool start level, you will get an error message and may not know what it pertains to. If everything looks good, select OK. Mach 1 first position is your machine position, better known as your work coordinate system. It might come out on the G code as a G54 or E1, depending on the type of machine you are using. If you right-click on the Mach or on the position, you will have a right-click menu to select from. We are not going to make any changes to the Mach, so let's select the green check. If you're only working with 2-axis and don't plan on ever using SolidVerify, which is just one of 8 options available in simulation, then the stock and target do not need to be defined. However, being that SolidVerify is one of the most powerful simulation options, you will likely want to get in the habit of defining the stock and the target. Let's select stock. In the Define By drop-down box, there are 5 different options for creating stock. Starting with the one at the bottom, you can browse to a location and select an STL to represent the stock. The next option can create a cylinder around the part using the Z-axis as the center line of your cylinder. When you select the model, it will draw the cylinder around the Z-axis according to the cylinder offset values at the bottom of the definition screen. Changing the values will update the live representation of the cylinder on the screen. Then you must choose Add to CAD Model to change the live representation of the cylinder into a 3D CAD entity, which is then created inside the CAM model. The next option is 3D Model, which is similar to the STL option. This option allows you to select an imported model as the stock. If you haven't imported a model for your stock or it hasn't been created yet, you can skip the stock definition until you've had a chance to either create or import one. You would then finalize the CAM project, go to the Feature Manager design tree, and create the 3D stock model or import one. Then come back to SolidCAM, select a 3D model option, and select the newly created model as the stock. Extruded boundary is similar to SolidWorks, where a chain can be defined and the profile will be automatically extruded up the height of the part. The last option, which is what the system defaults to, is the box option. Similar to cylinder, the box option will create a billet around the furthest extents of the part. The system defaults to relative to model, but absolute coordinates is also an option. Depending on the mode selection, the values you see under Expand Box At will be either relative to the model or absolute to the coordinate system. The green box you see on the screen after selecting the part is the live representation of the stock body and will update as you change the values. Once the size of the stock is achieved, you must select the Add Box to CAD model, which converts it to an actual CAD entity shown in the CAM part under the project assembly. If we scroll back up, we can select the Show button to render an STL 3D version of the part. If everything looks good, you can close the graphics window and accept the stock. The target can be automatically defined by selecting the check mark next to Definition of Target in the SolidCAM settings under Automatic CAM Part Definition. This may be something you will want to do if you are always working with individual parts. I am not set up for automatic target definition, so I will need to define my target. Select Define 3D Model. Now select the part or parts you want to define as the target. When you select the model, it will add Solid 1 in the white box under CAD Selection. To deselect, you can either choose the model again or right-click on the Solid 1 and choose Unselect. One page back, you have the option to show on model, which will highlight the model within the assembly. The show button renders an STL 3D model of the part. In the event you are getting strange toolpath or want to make sure you are using the correct target, you can use the show button to see what the system sees. Let's accept what we have and go back to the CAM part definition screen. The facet tolerance is for display purposes only and does not affect the G code. Depending on the amount of RAM and your computer's overall speed, this tolerance can affect how well your system runs. If this value is set too low, it will slow your system down. If set too high, some of the elements on the screen may look faceted. Changes made in the part settings will only affect this CAM project and will not affect the main SolidCAM settings. For example, this part may have SOLIDWORKS configurations that need to be associative to the CAM project. In this case, under synchronization, you can switch the option to associate the geometry with the current configuration. If all your CAM projects are going to have SOLIDWORKS configurations, then you may want to change that in the main SolidCAM settings to avoid changing this option each time. Let's finalize our CAM part settings by choosing the green check mark at the top left. At this point, we need to discuss where these files were created and what they consist of. We'll locate our part by right-clicking on the CAM part definition and select CAM part properties. Highlight the path under Directory, right-click again on the blue highlight and select Copy. Now open Windows Explorer by holding down the Windows key located in between the Control and Alt keys and pressing the letter E. Or if you are using Windows 7, you can select the yellow folder on the taskbar. Left-click once in an open area on the directory bar, then do a right-click and paste. This should paste the directory path we copied from SolidCAM into Windows Explorer. Now hit the Enter key and it should take you to the CAM part file folder. There will be at least 3 objects. First, there will be the SOLIDWORKS model the CAM project was started with. There should also be a file and a folder that by default will be the name of the CAM project. If you did not rename the CAM project at the beginning, it will inherit the name of the SOLIDWORKS file. In my case, my SOLIDWORKS file is called Sensor Housing. Thus, the file and the folder created will have this same name. The Sensor Housing PRT file is a pointer file that manages the files located in the Sensor Housing folder. Since I am at the beginning of my CAM project, there will only be a few files. As the project progresses, more files will be created in this folder. The cam.sld PRT file is an empty model SolidCAM creates, which is used for adding surfaces, solids, boundary curves, etc. In the event the SOLIDWORKS model has a revision, the design model, which is the perfect copy of the SOLIDWORKS part, will be updated. Any additions or subtractions made in the design model will be lost upon update. This is the reason for the CAM model. SolidCAM also creates an assembly of the project for the purposes of allowing work on an assembly or for using fixtures for gouge checking. If we go back to SOLIDWORKS and look at the models in the Feature Manager design tree, you will see the same files. At the top resides the assembly file. Below that is the CAM model, which subsequently has the stock we just created. And finally, the design model, which will show us all the CAD features that were used to create the SOLIDWORKS file, if the file was created natively. Or it will simply have a body called import. You may have multiple bodies called import if you imported an assembly file from a different CAD system. The SolidCAM hierarchy or tree structure is where the project is managed from. If we right-click at the top on the CAM part, there are several options. The first one takes you back into the CAM part definition, or we can double-click the CAM part, allowing changes to be made to the CAM part setup. However, the machine, coordinate system, stock, and target are also on the tree for easy access. The CAM part properties shows the information about the project, like file location, size, date of creation, etc. Change model reference can be used to import all your toolpaths from one project into a new CAM project. The best way to achieve this is to do a save as on the current CAM project as a new CAM project name. Then do a change model file reference and select the new SOLIDWORKS model you want to import the toolpaths into. Close is technically the proper way to close a CAM project. If working in compressed mode, you should always use the close command to properly close the file. Using the close command automatically zips the uncompressed CAM files into a single file, instead of the file and the folder we discussed earlier. This new file will be the name of the project with an extension of PRZ, which is identical to a zip file. You can right-click on the file and extract it with any unzipping program. Save As is the proper way to rename a CAM project. Never rename the PRT file or folder or any files within the folder from within Windows Explorer. This will scramble the project and make it unrecoverable. Let me be very clear about this. The only way you should ever rename a CAM project is from within SolidCAM using the Save As function. Save updated stock to STL is used for saving stock from one project to another. In the case you may be turning the part before milling it, you would create and finish the turning CAM project. Then use the Save Updated Stock to STL to save the updated stock information to an STL and then import it later when you're beginning the milling portion of the project. Documentation Toolsheets is used to generate a tool sheet listing all the tools used in a CAM project along with other pertinent information like cycle times, tool offsets, etc. There are 4 formats to choose from with unlimited configurations possible. All tool sheets are open source and fully customizable by the end user. The Capture Image command takes a snapshot of the part, which is then automatically inserted into the tool sheet. If you have a DNC plugin, this option allows you to access any third-party DNC program from here that is already installed on the computer. You can set the path to your DNC program in the SolidCAM settings. Synchronize is used while in manual mode. Since I'm set up for manual synchronization, if after an update I see the SOLIDWORKS rebuild icon over the top of my stock, target, or both, I would then use the Synchronize option to update the stock and the target. The next 4 options on the list are links to the online training videos. There are literally hundreds of online help videos you can access. To access them, you'll first need to register for a free online account. If you're having trouble with a file and would like to send it to tech support for help, use the Send To option to automatically zip all pertinent files, including the post, which will be dropped into an email and can be forwarded to the support department. The other option is to zip it up and put it in a folder with or without the machine simulation files. The last option is Cleanup CAM Part. Cleanup CAM Part gives you the option of removing items that are not currently being used in the system. Generally, this is done after you've completed your CAM part project. This is useful for shrinking the CAM part file size and for decluttering the CAM project. Looking back at the tree, you will notice that the machine, stock, and target all have brackets with names in them. This tells us visually that a post was selected and that the stock and the target have been defined. Since you must have a coordinate system defined in order to finalize the project, the CoordSys Manager will not have any brackets. The settings below the target are the same part settings we talked about that are also located on the CAM part definition screen. Let's select OK and go to Tool under Settings. This is where you can create, edit, and delete tools from this CAM project. However, the tools for this project do not need to be created beforehand. Tools can be created and edited while setting up the operation, as we will see later. However, if the same tool is used in more than one operation, it cannot be edited within an operation, but instead must be edited here. A machining process is just one way to cut down on programming time. In a machining process, multiple tools can be defined to perform a particular function, for example, tapping. Tapping generally consists of a spot drill or a center drill, a drill, and a tap. Used in a machine process, these tools can be grouped together to perform a tapping function, where each of the operations for that tool will automatically be created in the operations list. This is an advanced feature that we will discuss in a future training course. The Geometries folder is an empty container box that houses items that are not currently being used in the system. Some of the items may include a profile that was chained and named but later discarded. The profile will still exist until you delete it from the Geometries folder or use the Cleanup CAM part at the end of the project. After importing any models you want to use as fixtures, you can define them by right-clicking on the Operations node and select Define Fixtures at the bottom of the list. Then simply select on the models you want to use as the fixtures. Now, when you enter Solid Verify, the fixtures will be visible. If the tool or the tool holder should touch any of the fixtures in any way, the system will notify you of a crash. Now that we have a basic understanding of the SolidCAM tree structure, we will create a 2-axis toolpath and take it into verification. We'll start off with the traditional pocket operation. All the toolpath dialog pages look very similar. It doesn't matter if you are in a 2-axis, 5-axis, or even a turning operation, the toolpath dialog pages remain virtually the same. The white box area on the left is known as the workflow area, and depending on the complexity of the toolpath that is being created, there may be more or less options available for use. For example, a 2-axis toolpath will naturally have less options than a 5-axis toolpath. The workflow area is easy to follow. Simply start at the top and work your way down the list of options. Starting at the top with geometry. If you need another coordinate system, you can create one from here, or you could have created it before opening this operation. The drop-down list will give you access to all the work offsets you have previously created. Let's define our profile or profiles we want to cut. The panel on the left is dedicated to geometry selection. The first thing you should probably get in the habit of doing is naming the operation. I will call mine rough inside. If this part has configurations, and one of the configurations is what you want to cut, simply use the drop-down box to select the one you want. I'm going to select the top edge on the inside of my part. When selected, the edge will change colors and establish a vector on the profile. The vector indicates the direction the tool is going to move and the tool location start point. Depending on where the edge is selected, the vector may be on the opposite side of the curve. Once the first pick has been made, you will have access to the 4 commands next to the chain list window, which are undo, reverse, accept, or delete. If the vector needs to be flipped, you would select the reverse button to flip the vector to the opposite end of the curve. Since SolidCAM defaults to climb mill, avoid more mouse clicks by selecting the edge in the correct location. In 2-axis, we will select the Z height and the depth of the cut, which means we do not need to keep our profile on the same level. I can move up and down in the Z as I pick my profile. Along with the ability to pick different Z levels, you have multiple options on the left for picking profiles. SolidCAM defaults to curve, which will allow me to simply pick each curve around my profile. Curve plus close corners will project 2 perpendicular lines to intersect each other. This can be used to create a sharp corner even if the part was not drawn that way. Loop simply finds the chain in all available planes, allowing the user to select the preferred chain. In this case, I want the blue chain around the top inside of my part. Point to point will allow selection of either points or endpoints of all elements. As long as there is a physical place to select, point to point can be used. This method is good for jumping small or large gaps that may be present in the profile. Arc by points inserts an arc using the current endpoint of the chain and the next 2 selection points. Auto 2 is used to automatically chain a profile. Auto General and Auto Constant Z work similar to each other. First select the Auto 2 box, then choose either Auto General or Auto Constant Z, and select the last element in the profile's chain. If the last element is not on the same Z level, you will want to choose Auto General. This method will stop at every intersection point and will require you to decide which way the chain goes by selecting one of the elements it highlights. Auto Constant Z is used to chain a partial profile instead of chaining the profile all the way around. Auto Delta Z automatically selects the entire chain in that plane based on the second pick that you make. Multi-chain is used to select all the sketch elements from a particular SOLIDWORKS feature. The elements will then be added into the chain list window, where you can either use or delete any of the elements you want to cut. If there are a lot of profiles in a particular sketch you want to use, it may be easier to select the sketch than to individually pick each profile on the part. The wrap feature under Options will wrap a profile around a cylinder. This is a more advanced option we will not be talking about today. I'm going to delete my profiles and simply use the top edge of the inside of my part as my pocket chain. Next, we'll need to select our tool. If we want to gouge check against a holder, we'll need to select a holder as well, but a holder is not mandatory. The two options available are Import or Add. I am going to add a tool. I will grab an end mill from the different types of tools, then define the tool's parameters. A good habit to get into is remembering to name the tool something that makes it easy to identify later when picking it from the library. Since tool libraries can be shared across the network, you may want to determine a naming convention that will be used throughout the engineering department. The description field is a verbatim text field, which means you can type special characters, wingdings, etc. to help in whatever naming convention you go with. I'm going to give it a basic name. The tool parameters are set in the Topology tab, which is one of multiple tabs below the description field. Selecting the diameter field automatically highlights the parameter on the tool. Subsequently, you can highlight the parameter on the tool, which will automatically select the associated tool field. The overall tool length is set at 3 inches, and the tool is hanging out of the holder by 2.5. As I mentioned before, we do not need to define a holder, but if we do, SolidCAM will automatically gouge check against it. For training purposes, we will select a tool holder. The system comes predefined with some common sizes and types of holders. If the current holders don't represent what you are currently using, you can define a custom holder by drawing the profile of the holder inside SOLIDWORKS, and SolidCAM will revolve it into a solid holder. This is something we will discuss in a future class. A custom tool can also be defined using the same method, then imported into the Shape tab. I'm going to turn on the Show Tool icon to see the live representation of the tool based on the tool's parameters. As you can see, if I change how much of the tool is hanging out of the holder, the live representation will update. I'm going to update my number of flutes to match my description. The number of flutes will matter if the feed rate is going to be based on inches per flute. Inches per minute is dynamically linked to the inches per tooth. Likewise, the RPM is dynamically linked to the feet per minute. If I type 600 in the feet per minute field, then select the RPM radio button, you can see that 600 feet per minute equates to a little over 4,500 RPM. If you need a separate feed and speed for finishing, when doing a finishing pass in the same roughing operation, you can check the feed finish and the spin finish boxes to define the finishing values. In the Coolant tab, there will be red X's and green check marks to show you what coolant options have been enabled in this particular post. If they do not accurately represent your machine coolant options, they can be adjusted in the post. Along with the description field, up to 5 more messages can be output in the G-code as a comment. I'm going to go ahead and accept this tool. Now we need to select the levels. When we select any of the fields, you can see the picture at the bottom left of the tool page will update. Most fields and radio buttons you select in SolidCAM will give visual help as to what that particular field does. This is extremely helpful in more advanced toolpaths. You can type in a value for the upper level, but if there's a button available, I highly suggest using the button. Using the button will help prevent mistyped numbers and give you a deeper level of associativity, as long as you select a vertex or a face on the part. The fields will turn red when they have been associated with the design model. The delta depth is an absolute field, which means either a positive or a negative value can be used. Any amount left in this field will either be added or subtracted from the level when the operation has finished. The pocket depth is subtracted from the upper level and shown in the pocket depth field. By default, the step-down value is calculated from the tool. You can change the value or right-click in the field and choose a math function for calculating the step-down value. Equal step down, if chosen, divides the pocket depth by the step down amount. If the pocket depth cannot be evenly divided by the step down amount, the value is rounded up to the nearest whole number. Then that number is divided into the pocket depth, which is then used as the step down amount. The step down amount always shows the desired maximum step down, but the field is now titled Max Step Down, which means the step down amount will never exceed that value. The technology page determines how the geometry is going to be cut. For example, the pocket pattern, standard pocketing versus rest material or chamfering, offsets, rough versus finish passes, compensation, etc. All that is set here in the technology page. This will be covered in detail at the beginning of the second class, SolidCAM Basics. When I select Save and Calculate, it generates the toolpath under the Operations folder in the SolidCAM tree. To view the toolpath on the screen, put a check in the box next to the operation. Now let's open the Simulation panel by selecting Simulate next to Save and Calculate. There are 8 different modes of verification. The one we will be looking at today is Solid Verify. Show Data should be turned on by default, but can be turned off by deselecting the Show Data box. The Show Data gives valuable information about the cycle, including total estimated cycle time. Solid Verify has many options to choose from, one of which is called Automatic Stock Update. Automatic Stock Update, which can be turned on and off by toggling the icon on the lower bar all the way to the right. Let's say you have 10 toolpath operations that you have already defined and you want to run verification on the 7th toolpath. When you open Solid Verify, the stock model will automatically update to show the previous 6 toolpaths in the operations, letting you clearly see what the model looks like up to that point. Because Solid Verify is commonly used, there are a couple of settings we should discuss. Above both rows of icons is File, Options, Settings, and Tools. Let's go into Settings, General. The first thing to do is go to the bottom left and select the Defaults button to make sure all the defaults are reloaded. Then change the Move Tool Redraw interval to 1. By default, Solid Verify is set up to draw the tool every 15th move. This can make verification look very choppy. Setting it to 1 may slow down verification slightly, but will also make the verification smoother. Let's select Settings, Accuracy. The tool facet tolerance can also affect how fast verification runs, but also has an effect on how faceted, rounded areas on the part will look after they have been verified. How the model initially looks when you enter Solid Verify is based on the facet tolerance we talked about on the CAM part definition screen. This concludes our time for today. Thank you for joining me for Introduction to SolidCAM Part 2, Menus and File Management. Please join me for SolidCAM Basics Part 1, Programming, to continue where Menus and File Management leaves off. If you are viewing this video during a webinar, please visit us on the web and register for a free account to access more online help.